Welcome back. The purpose of this video is to describe the main results for principal components analysis. I want you to understand how PCA finds the subspace with a little bit more rigor. In my subsequent video, I'm going to walk us through many examples of how PCA gets applied to various data sets. And we're going to see how to estimate it in R, perhaps with other software packages. And in order to use those software packages, there's a lot of options that you will have to know about, and you really need to understand a little bit about how PCA works in order to choose the right options. All right, so before I get to the main results of PCA, we need a little bit of review about covariances and correlations. So PCA is going to analyze the correlation of the covariance matrix. So what does that mean? Well, on this slide, I've summarized some basic facts about covariances and correlations. I might reference my basic stats lecture on this if you want to watch that. You can get that video as well. But let's say I've got an n by p matrix X. So let's just go draw it. So here's my X. So it's the same matrix we've seen 100 times in here. My first subscript is always going to be the row. The second subscript will always be the column. And I have p of these columns. So this is going to be 1p through x np. Let's just close that's a closing parentheses. I think I ran out of space there. And so there's our matrix. So x bar 1j is going to be the column mean. So if this is column j, so this would be x 1j through x nj, we can find the mean of that column. So we just call that x bar j 1 over n sum I equals 1 to n x ij. So in other words, that's a lot of fancy math language for add up these values, divide by n. Then the next thing we would have learned back in basic stats is, well, what's the variance of that column? Are all these values about the same, or do they vary a lot? And so the way we usually summarize that is with the sample variance. I'm going to call x squared j the sample variance of column j. So we just add up the squared deviations in that column, divide by n minus 1, and that's our estimate of the variance. Well, a little bit later on, once you get to two random variables, you would have studied covariances. So covariances talk about how one column or variable goes with another column. So the way we compute a covariance is, or the way we estimate one is maybe a better way to describe this. If I want to estimate the covariance between columns j and k, I'm just going to mean center both my variables. So take every value in the jth column and find out how far that is from the mean. Do the same thing for column k. Then I multiply them. And then I add up those products and divide by n minus 1. So if x1 is above average when, xj is above average when xk is above average, then these would all be positive, and if I had xj negative when xk was negative, the product would be positive, and we would have a big positive number. So maybe a picture is worth all those words that I was saying. So let's say my scatter plot looks like this. This is xj, this is xk. So notice whenever xj is above average, so is xk. When xj is negative, so is xk. So the product is positive, the product is positive. I average a bunch of positive numbers, I get a big positive number. If I had a situation where the correlation went the other way, notice all of these products would be negative, all those products would be negative. The covariance would be negative then. All right, so I'm going to use this should be s squared. I'll fix that before that's not s squared. That's the sample covariance between columns j and k. All right. We're going to represent the covariance matrix, which is going to be p variables by p variables, by a big, bold S. And so that's going to be a P by P matrix consisting of all of the variances and covariances. Now, I want to give a couple results around this. The first one is whenever my columns of X are mean-centered, then if I take X transpose X and I divide by n minus 1, I get the covariance matrix. So important to note, when X is mean-centered, I get the covariance matrix when I compute this product. I'm just going to jump ahead when they are standardized. So if I compute z-scores for each column, then I get the correlation matrix. But more on that in a second. Let me work through an example now to illustrate this. So let's just say that P is equal to 2. Now, what I'm going to do is compute X minus its mean. So I'm going to write this like this. I'm going to take every X minus the mean transpose times X minus the mean. So let me write this out exactly what it looks like to make my notation clear. So what I basically have here is X1, 1 minus X bar 1. So this is going to be the first entry minus the column mean of that. This would be X21 minus X bar 1 all the way through Xn1 minus X bar 1. So that's the first column of this matrix right here. And then let's take X12 minus the column mean for the second column, which would be X bar 2. This would be X22 minus X bar 2 all the way through Xn2 minus X bar 2. And then let's close our parenthesis. Then I have to compute the transpose of this. So I'm not going to write it all out. We're just going to give ourselves a couple terms. This would be X11 minus X bar 1. That's that term. And can I just say dot, dot, dot all the way through to this guy? So Xn1 minus X bar 1. Then this one is going to be, well, X12 minus X bar 2 dot, dot, dot Xn2, so through this term down here, minus X bar 2. So now if I compute this product, let's see what I get. I'm going to get a 2 by 2 matrix, which is equal to, I have to add from I equals 1 to n. So we're going to take this term times this term plus this term times this term all the way through the last term times the last term. So this is going to be the sum of xi1 minus x bar 1 squared. That's that first entry. Now let's go do the second entry. So this one's going to be the sum, again, I equals 1 to n. And this is going to be xi1 minus x bar 1. So that's that term. That's that term. Now we have to multiply it by this term. So this would be x12 minus x bar 2. If I do the other top one, well, let's see, that would be this times this. And I would get the sum of, well, xi1 minus x bar 1 times xi2 minus x bar 2. And again, my subscripts go from 1 to n. Then what is this bottom entry? I would take this times this plus, well, the next term all the way through the last term, and I'd end up with something like this. I equals 1 to n, xi2 minus x bar 2 squared. And that's my matrix. Well, does this look familiar? Well, it should, because what we clearly have is this is that exact same sum that I had when I computed my variances. This is the exact same sum that I have when I compute my covariances. All right, so what I claimed down here was if I take, gotta be able to see it, sorry about that. If I take x transpose x, well, let me start out by saying if x is column mean-centered. So what that means is I've subtracted the means of the columns just as I did upstairs. And I divide that by n minus 1, then clearly I get my covariance matrix as we see up here. All right, these two terms. So what you need to know is that if you have mean-centered x's, that x transpose x matrix is just the covariance matrix. Now, let me review what a correlation matrix is. Correlation matrices are where we divide the covariances by the product of the standard deviations. So here's the product of the standard deviations. So we usually we call our sample covariance matrix R. So the population covariance matrix is usually rho, or population correlation would be rho. Sample is R. So the theorem is, if I had columns that are standardized, where I've divided by these standard deviations, then if I take x transpose x, divide by n minus 1, I get the correlation matrix. Okay, so let's just summarize the big idea here. If I have mean-centered x's, mean-centered x's gives me the correlation, the covariance matrix. Standardized x's gives me the correlation matrix. All right, let's go to the next page. Here are the main results. We're going to assume that my columns have been either mean-centered or standardized. So that's why I made us go through that previous page in detail. And so rather than trying to write some notation to indicate that the mean's been subtracted, I'm just going to say we've already done that. So that happens as a pre-processing step. We mean center things, or we also divide by the standard deviations to get the standardized values. So then, of course, we have either the covariance or the correlation matrix. So the first principal components analysis, first principal component from PCA can be found with either one of these objective functions. So the first objective function is to minimize the sum of squared distances. So this is the squared distance between x and the projection of x onto u. So we're going to pick this this first principal component direction to minimize that that orthogonal deviation. So I've already drawn this in my previous videos on PCA, but if this were my scatter plot, what that's really saying is pick the subspace so that these vertical deviations, some of these square vertical deviations, is as small as possible. So I've said that already in one of my earlier videos, but now you have the math showing it. Alternatively, we could phrase this as a maximization problem, where I want to maximize the variance of x transpose u. So what's x transpose u? Remember, if we go back to this result on projections, x transpose u is the length of the projection of x onto u. So the way you should be thinking about this is x transpose u is the first principal component or the coordinate. So it's saying, if this is my x, remember that's a vector x, and this is my u vector. This is going to be the projection of x onto u. And this length right here is x transpose times u. So x transpose u gives us that length. And so what I want to do is maximize the variance of these lengths under the constraint that u is a unit length vector. If you don't have u as a unit length vector, then this problem is not very interesting, because we could simply make our u a very short vector then the lengths, of course, become very big with respect to that short u. So we're going to put this on, make this a constraint that, you know, the length of this u vector is 1. Then what I want to do is maximize the variance of the scores. So let's just consider an alternative one. If I chose, say, this is a u, all right, this is just some other u, and I start projecting all these points onto this, what I'd like you to note is that the variance of these lengths is much smaller than the variance of the lengths when I chose that other direction. So either of those ways give us the first principal component, and the second principal component is going to be solve the same optimization problem, whichever one you chose, with the constraint that whatever that second vector is has to be orthogonal to the previous one. So in this example, I think we need to start out with a new scatter plot to show this a little bit more clearly. If this is my first u, so that's my first principal axis, we could call this the first principal axis. The second principal axis is going to be the one that is orthogonal to this. So this would be the second axis, and we could describe that with a vector that goes this direction or with a vector that goes this direction. Doesn't really matter. It's describing the same axis. All right, then if we were up in p dimensions, now this is not very interesting in 2 dimensions because there's only one direction that's orthogonal to this one, but if we were up in, say, 3 dimensions, then it becomes a little bit more challenging to find that. If we were in p dimensions, I could repeat this p times to get my my vectors. All right, so that's the way we define our principal components and these principal axes. Question, how do we estimate them? So I'm just going to state a theorem and maybe derive this in a later video. The solution to this is given by something called eigenvalues and eigenvectors. Now, you would not have seen eigenvalues and eigenvectors unless you took a full-length course in linear algebra, and typically you don't get to the eigenvalue chapter until late in the course, so often it gets dropped from sort of an intro course on linear algebra. I don't want to get into what an eigenvalue and an eigenvector is in this video. I'll try to give you a little bit of intuition in a later video, but what I'd like for you to trust me on right now is that there are things called eigenvalues and eigenvectors. So eigenvalues we're always going to represent with the Greek letter lambda, and I'm going to order my eigenvalues from largest to smallest. So in this class, at least on the unsupervised learning part, lambda 1 is always the biggest eigenvalue, and lambda p will be our smallest eigenvalue. So these are eigenvalues of either the covariance matrix or the correlation matrix, depending on which one we chose. Then there's going to be a set of vectors that go with these eigenvalues. So for every eigenvalue, there's a pair, they're in pairs. There's an eigenvector. So these gammas are going to be my eigenvectors. So I've been calling my basis u up until now, unless I had a special basis like the standard basis I called e's. Now I'm going to call my these eigenvector basis vectors gammas. So whenever you see a gamma now, that means it's an eigenvector, and it's going to be one of these principal directions, principal axes directions. All right, couple really important points. I'm just going to state these as theorems, and then again, maybe I'll prove them in a subsequent video for those of you who are interested. But the principal components are going to be x times these eigenvectors. So if you go back to, I said this was an important result back couple last lecture. These u's, so u is just a general basis vector. We're going to replace that with this special one that we've estimated, the eigenvector. These are going to give us our principal component scores. And then it turns out the variance of these scores, so remember I said one of our objectives, so here's your principal component score. The variance of this is given by the eigenvalues, the lambdas. So let me go over to my piece of paper here and just try to, reinforce the intuition. So if you think about the variance in this direction, so the variance of, or the variance for the scores in this direction is going to be lambda 1. Now you could think about the variance of the scores in this direction as lambda 2. So lambda 1 is clearly much bigger. There's much more variance in this direction than the variance in that direction. So that's what these lambdas are telling us. Let me just review what the principal component score is. So if this is, for example, an x, then the projection of this onto my first principal axis, we're going to say is this first principal component, which I'm calling y1, which is the first PC. So that's the first PC right here is the first principal component. The deviation in the other direction is the second principal component. So that's the first principal component, the second principal component. The lambdas tell us the variance. Now, another thing that we often want to be able to say is how much variance have we summarized with this principal component solution? And so it's kind of like an R-squared measure. So R-squared gives the fraction of variation in y that's explained by your x's. Well, we're going to have something really comparable, which is going to be the fraction or proportion of variance explained by the first k components. And the way we get that is we just add up the first k eigenvalues and divide by the sum of all eigenvalues. So I'm going to just go over to my piece of paper here and draw a little picture. So let's say I had some points that look like this. And so I've rigged it so that these points exactly fall on a line. So what would be my first principal component? Well, the first principal component is this. This would be my second, well, this would be the first principal axis. This would be my second principal axis. Now, what I'd like for you to note is there is no variance in this direction. So lambda 2 would be 0. So there's no variance in this direction, whereas lambda 1 is going to be fairly big. So what I just said is we're going to take, if I want to look at what fraction of variance do I capture with the first principal component, I'm going to take lambda 1 divided by lambda 1 plus lambda 2. So this is going to be lambda 1 over lambda 1, since this is equal to 0, which is 100%. So in other words, I would capture 100% of the variance in my data by summarizing it with the first principal component. So knowing the lengths of the projections onto this line, we don't have to project much because they all fall in the line, but just knowing how far each one of these points are from the origin tells us everything we need to know about these x's. So we would say we're capturing 100% of the variance there. All right, so those are the main results. Oh, there's one other thing I want to mention. Very important thing, which is when do I use a just mean-centered x versus a standardized x? The answer to that question is it depends on your units of measure. So if you have different units of measure, like x1 might be measured in centimeters and x2 might be measured in degrees Celsius. Well, those are different units of measurement, and I can't compare centimeters with degrees Celsius. What we tend to do when we have incommensurate units is just standardize it. Alternatively, if I have commensurate units, so x1 is measured in centimeters and x2 is measured in centimeters, I could make a case for not standardizing and just mean centering. All right, so the rule is if you have incommensurate units, you want to standardize. If you have commensurate units, then you probably don't want to standardize. You just use the covariance matrix, not the correlation matrix. All right, that's it. We're going to come back in the next video and apply this to a lot of real problems. Hope to see you back.